Hello, welcome back everyone. In this video, I'll show you some of the modifications that you can carry out on the quadric surfaces. All these while the quadric surfaces that you have been looking at are in their standard form. Now, there are three modifications that we can carry out on the quadric surfaces. The first one is transformation, second is translation, and the third is reflection. The first one, transformation, which means that the value of the a or b coefficients in front of the x square and y square can be changed. Recall back from the previous video where we took the elliptic paraboloid as an example. When you vary the coefficient of a and the value of coefficient of b, you will realize that the elliptic paraboloid will be distorted in a certain way. So it is almost impossible for us to sketch it out using our hand, and that's why I'm going to skip this part. If you have forgotten on how the values of a and b, the coefficients in front of x square and y square, will affect the shape of the quadric surfaces, try to watch back the video that I prepared for you in the previous lesson, or you try to explore in the interactive gallery. For the second modifications, which is the translation, where the vertex of the original quadric surfaces will be shifted to another position. Now, let's recall back how to sketch a 3D quadric surface. We'll use the elliptic parabola as our example, our favorite example here. This is the typical equations for an elliptic paraboloid. The first step is to sketch the x, y, and z axis, and we decide the vertex of the elliptic paraboloid. How do we know that the vertex is at 0, 0, 0? Well, apparently when the x equals 0 and y equals 0, z will be 0. And how do we know that the body of the elliptic parabola is in such a form? Recall back from the previous lesson, the interactive gallery. When you cut across the elliptic parabola with a constant or a plane of z equals to a constant value, what curve would you get? You'll get a traces or a mesh lines with different radius of circle, right? Because when you substitute the z value with a constant, you end up with the equation for circle. So when the values of x and y are getting larger, the radius of the circle will be larger as well. So you have this shape where the orientation of the circle, orientation of the elliptic parabola is in the positive z direction. Now, what if the new equations given for the elliptic parabola is in this form? Z equals to, in the bracket, x minus 1 square plus y plus 3 square minus 1. So this equation actually resembles the elliptic paraboloid equations, but we need to rearrange the equations first. You move the negative 1 to the other side, so you end up with z plus 1 equals to x minus 1 square plus y plus 3 square, which resemble the standard equation for elliptic paraboloid. Remember, the vertex for the original elliptic parabola is 0, 0, 0. Now, since this equation shows that the elliptic paraboloid has been shifted to another new position, how are we going to find out the new vertex of the elliptic paraboloid? It's pretty straightforward. You just need to equal the z, the x, and the y terms equals 0, and you'll get the new position. So for the x minus 1 equals 0, so x is 1, y plus 3 equals 0, and y is negative 3, and z plus 1 is equals to 0. So z is negative 1, and this coordinate is actually the new vertex of the elliptic paraboloid. And you sketch it by drawing out the x, y, and z axis and identify the new vertex, which is somewhere around here. Positive 1 x, negative 3 for y, and negative 1 for z. So your new vertex will be in this position. And you know that these equations, this elliptic parabola will always be positive. The orientations will be upwards to the positive z direction. So you just need to draw out the body of the elliptic parabola in this way, and you get it. The third type of the modifications that you can carry out on the quadric surfaces is reflection. Now look at these equations. It is actually similar to the elliptic parabola, but we have a minus sign here, which means that for every x and y value, you will get a negative value for z. So it's actually the flip or the inverse image of the standard elliptic parabola. So you just need to flip it across the xy plane and you have this elliptic parabola. And all this while, we express the quadric surface in the form of z or z squared equals to x squared and y squared. What would happen if we swap the position of the terms here? Just take a look at this example, x equals to z squared plus y squared. It is actually quite similar to the standard elliptic parabola, z equals to x squared plus y squared, but the z and the x has been swapped for their position. So which means that the opening will be in a different directions. How do we know in which direction the opening should face? The opening of the elliptic parabola. And one simple example, remember the meshed lines, the traces in the previous video where we determine the intersection curve. We cut across the quadric surface with a plane. Now, using this concept, you try to substitute the value of x with a constant. So you will end up with a z squared plus y squared equals the constant. It's actually an equation of circle, which means that the circle is on the plane of z and y. And when you vary the value of x, you'll get a different size of circle. So the opening should be towards the positive x direction as shown in this direction. Last but not least, consider this equation. This transformation involves translation and reflections together. So try it out and pause it out in the comment section to test your understanding. Let me give you some tips on how to solve this question. The first step is to check on which type of surface that this equation resembles. The second is to determine the orientation and the directions of the opening of the quadric surface. And the third is to look at the new vertex. So by combining these and the steps to draw or to sketch a 3D quadric surface, I believe that you can solve this equation easily. Thank you.